So in science, the word spontaneous means something that happens without us having to do anything. No outside intervention needs to happen. You set out, for example, hydrogen peroxide, and it will spontaneously decompose into water and oxygen gas. That doesn't mean it happens fast, but it does happen. And so what we do is in order to know if that's going to happen or not, we need to use both thermodynamics and chemical kinetics to figure out if it's going to happen and how it's going to happen. So in the thermodynamics, we look at what the final state is, what the initial state is, and compare those two things to see if it'll be spontaneous. And in kinetics, we try to figure out what the exact pathway is, what the first products are and the intermediate products and what the final products are, and we figure out the exact reaction pathway for those things. Now, if you think about some things, spontaneity is easy to predict. You put an ice cube on the table in the classroom and it will melt spontaneously. We don't have to do anything. It will automatically change from solid to liquid all on its own. And keep in mind the first law of thermodynamics. The energy of the universe is constant. Energy is conserved. So we keep track of thermodynamics, but that doesn't always predict spontaneity. Exothermic reactions tend to be spontaneous because it lowers the energy of the system, and systems tend toward lower energy. However, melting an ice cube is endothermic. Energy has to flow in for that to happen. So that reverses our expectation of what the thermodynamics would predict. So we have to introduce a new measurement, and that's entropy. Entropy, the symbol is capital S, is the measure of the disorder or randomness of a system. And so we have to take into account both the thermodynamics, the enthalpy, the delta H, and the entropy, the disorder of the system, to determine which is going to determine if it's spontaneous or not. And so now we get to the second law of thermodynamics. The second law says that the entropy or the disorder or the randomness of the universe increases. Okay, it tends toward the maximum. It's always increasing. Every change that's spontaneous will increase the entropy of the system or of the universe. It's always tending toward the maximum. Now, we can decrease entropy in local areas by increasing the entropy around it. But overall, the entropy of the universe is always tending toward a maximum. It's always increasing. Entropy is defined in terms of probabilities. And if you've had statistics and probabilities, you know way more about it than you need for this class. All you have to know in here is that substances will take the arrangement that's most likely, which is the most random position. If you throw a deck of cards up into the air, it's not very likely that they're all going to land in order, by suit, stacked up neatly. That's not the most likely arrangement. They're going to be spread out. They're going to be random. Random is most likely. And we can, for small systems, small numbers of things, we can actually calculate the number of arrangements that we can have in that. So for example, if we have one atom in a system, and there's two places it can be on the left, or it can be on the right. There's a 50-50 chance of finding it on either side. However, if we have two atoms in the same system, two connected vessels here, we can have both on the right, both on the left. We can have red on one side, yellow on the other, or switch them. So there's a 25% chance of finding the left side empty, a 25% chance of finding the right side empty, or a 50% chance of having one in each. So what's most likely? Having one in each. The entropy says that it's most likely to find one atom on each side, not two on the same side. And that's just simple probabilities, calculations here. If we have a more complex system with 4 atoms, we could have the left side empty or the right side empty, but that's 1 out of 12 possibilities. Okay? We could have 1 in either side, and that's 4 out of 12, so that's a third chance of having 1 in a side. Or if we have 2 on each side, we actually have a 50% chance of them being evenly dispersed. What's most likely? 8%, 33%, or 50%? 50%. It's more likely to be spread out as much as possible. That's entropy winning this argument, winning this race here. So gases, this is why gases expand. One of the reasons gases expand to fill their containers. It all has to do with entropy. There are more ways to fill a container with gas particles than to leave it empty and have them all squished down into one side. So if you look at the entropy of different phases, gases have the largest entropy of the phases, and the double less than means much. Liquid is much less entropy than gas because they're all packed together, and solid is less entropy than liquid. That's what the less thans are for, because there's more ways for the molecules to rearrange and shuffle in a liquid because they're free to move past each other than in a solid. And gases have even more possibilities because they're not bonded to each other, they're not attracted to each other at all. So when we dissolve something, like if we put salt in water, it will spontaneously dissolve because of entropy. There are more arrangements of the dissolved particles floating around than if they stayed together as a crystal. So if we look at the second law as a formula, remember every law in science has a formula associated with it. The delta S, the change in entropy of the universe, is equal to the change of entropy of the system plus the change in entropy for the surroundings, which makes sense. System and surroundings make up the entire universe. So if the change in entropy of the universe is positive, we're going to call that spontaneous. If the change in entropy of the universe is negative, well, it's not spontaneous. It's spontaneous in the reverse. So we can look at reverse reactions here. So in an exothermic process, the change in entropy of the surroundings is usually positive. Why is that positive? As heat goes out into the surroundings, exothermic heat energy is going out into the surroundings become hotter. What happens when the temperature increases of the surroundings? The particles are moving faster. As the particles are moving faster, they're able to rearrange themselves into more random positions. And I don't mean just that the randomness is bigger, but there are more positions they can get themselves into because they're moving faster. And so the delta S of the surroundings is increasing. Endothermic is the opposite. As heat flows in, the surroundings cool down, the particles slow down, which means they are less random. They are able to take fewer positions. So let's take a look at water evaporating. H2O liquid going to H2O gas. Okay, in order for this to happen, this is an endothermic process. We are putting energy into the system to make it evaporate, right? It has to get more energy to escape the liquid phase to become a gas. So the change in entropy of the system is positive. Liquid is less entropy, gas is more entropy. So as it goes from liquid to gas, the delta S is positive. It's increasing its entropy, which means the surroundings are decreasing because we're putting energy into it. Now, the delta S of the universe depends on the temperature, right? At high temperature, this happens very well. At low enough temperature, it actually happens in reverse. This is why we get dew on grass or condensation on the outside of our cold soda bottles. If the temperature is low enough, the spontaneity reverses. So there's some temperature dependence with spontaneity and entropy. And we'll explore that in the next set of notes.